Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Numerical Investigation and Simulation of Impact Energy Absorption by Materials in Ballstic Mohammed Imran Mechanical Engineering Department, ME, Mohammed College of Engineering and Technology, Hyderabad, India Dr. K. Hemalatha, Associate Professor Mechanical Engineering Department, ME, Mohammed College of Engineering and Technology, Hyderabad, India Abstract. This report treats terminal ballistics, which is the branch of the ballistic science concerning the mechanics of impact. The purpose of this project is to determine the parameters governing projectile failure when impact against a target is achieved and energy loss of projectile in each layer of composite are observed. In the simulation approach, a model has been derived capable of determining the amount of deformation in the projectile after impact, energy summary in each layer, and simulation method of obtaining the resistance pressure, by which the target resists penetration, and a method of determining the energy loss projectile material are also implemented. A numerical section explaining the main factors and approaches in hydrocode and dynamic modeling is also devised along with simulations of projectile impact. Keywords: ballistics, projectile, and target, penetration depth, projectile failure. Introduction. In ballistics, the protection from the targeted projectile requires loss of energy or absorption of energy of projectile by protected material. Today modern projectiles are more advanced, powerful, high velocity and high energy objects which can damage the targeted object in seconds. To protect the object from the powerful projectile we require strong and highly advanced material on the surface which can cover the whole body of the object. Modern defense system associated with advanced technology in material science which can be used to selection of materials for design the system. Material selection plays vital role in the design of any system. Material selection is depend on the type of the object, where can be used and how it can be used. Surrounding systems around the object effect on the object material and it can be leads decreases the lifespan the object. In advanced systems most of the materials used are combination materials like alloys and composites. Materials possess different properties based on the conditions it can also affect the system. 2 Materials and methods. Materials requires for system is the important decision for the design. Materials for ballistics requires highly strength and hard. Composites and alloys are widely used for design process. 4 Strong materials can possess high density, low weight, high hardness etc. Energy absorption of materials require high density, fracture toughness, and strength. Fracture toughness is the important property for absorption of energy. Fracture toughness is determined by impact test. In modern system considering all the conditions we require high density, fracture toughness, high stiffness, low density, and highly ductile material. Aluminum foam and Kevlar are tested for this purpose. Table1. Properties of materials. S layers of density. No armor, kg/m3, Young's Poisson modulus ratio. Yield stress specific heat plate, GPa, J/kgk, 1 Kevlar 1440 91 0.3217 710 2 Aluminio 700 100 0.33 140 950 M Foam. Kevlar poses good absorption of energy property, chemically inactive, low thermal conductivity properties. It has high resistance to stop object and it can leads loss of energy in the object which may decrease the damage of system. Aluminum foam is highly ductile and low weight. It can decreases velocity of the object. These 2 materials are used in ballistic protection system as hybrid composite. Fig. 1. Aluminum foam. Fig. 2. Kevlar layer 3. Numerical calculation. Energy absorption by the layer equals fracture toughness of the material x area of penetration by bullet, / thickness of the layer penetrated by the bullet. IJERT 10 is 060190 www.ijert.org 442. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. E equals FTXAXLT. F equals fracture toughness of the layer. EA equals absorption energy by layer. A equals area of cross section of bullet. L equals distance between target and observer. T equals thickness of layer. Total energy equals absorption energy by the Kevlar plus remaining energy. Remaining energy equals force on the second layer. Absorption energy by the layer equals kinetic energy absorbed. Absorption energy equals 1/2 m 6 superscript 2 Vr superscript 2. Vr equals residual velocity of projectile. 6 equals initial velocity of projectile. Fig 4.2 mm thickness energy absorption energy at the present at the surface layer by bullet equals 1/2 m VE. M equals mass of the projectile. VE equals velocity present at the surface. In numerical calculation, energies and velocities are determined. Energy absorption in the material is approximated by the given formula. The mass of the bullet taken as 10 grams. The velocity attained by the bullet from the gun barrel taken as 854 m/s. The residual velocity of the bullet calculated by the theoretical formulation. Thickness of the layers of material is varied and absorption energies are calculated. The distance between the targeted object and gun barrel taken as 1 meter and it is taken as length in the formula. Fracture toughness is the material property used in the formula and other values are depends on geometry and velocity. Fig 5.4 mm thickness energy absorption 4. Design and simulation. Kevlar layer, Fig 6.6 mm thickness energy absorption. Fig 3. Kevlar layer meshing. Fig 7.8 mm thickness energy absorption. IJERT 10 is 060190 www.ijert.org 443. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig 8.10 mm thickness energy absorption aluminum foam, Fig 12.26 mm thickness energy absorption. Fig 9.2 mm thickness. Fig 13.24 mm thickness energy absorption. Fig 10.30 mm thickness energy absorption. Fig 14.22 mm thickness energy absorption. Fig 11.28 mm thickness energy absorption. Fig 15.15 mm thickness energy absorption. IJERT 10 is 060190. www.ijert.org 444. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 V. Results and discussion. Energy absorption of material determined by numerical investigation and simulation methods. In numerical method, fracture toughness is the important property for calculations. Energy absorption varies by thickness of layer, and increasing the layer thickness increases the loss of energy of the projectile. In numerical and simulation methods we also calculate velocities of the projectile, which is used calculate energies. For simulation method we are used LS Autodyna in ANSYS workbench. Initial conditions, boundary conditions plat predominant role to get exact values. Energy absorption of material increases the thickness of the material, but it increases the thickness and weight of the system. Considering the conditions we optimize the thickness and weight, it increases the efficiency of the system performance. Table 3. Aluminum foam energy absorption at various thickness S. No layer thickness energy loss, joules, velocity, mm, reduction, m/s, 13469 306.32 28 442 297.13 26 418 289.24 24 386 278.55 22 352 265.26 15 258 227.6 TABLE2. Kevlar energy absorption at various thickness S. Layer thickness energy loss no, mm, joules, 12251 24 373 6 585 48 710 510 861 6 15 945 velocity reduction, m/s, 29.3 45.1 72.3 88.6 109.2 120.5 Fig 18. Thickness vs velocity Fig 16. Thickness vs velocity Fig 17. Thickness vs energy absorption Fig 19. Thickness vs energy absorption 6. Conclusion: this is aims towards better efficiency of material layers and also identifies the optimum thickness of layers, which also affect on weight reduction of ballistic armor. Efficiency of performance is maximum at optimal conditions. Kevlar and aluminum foam are the materials used for ballistic protection system. High density, stiffness, elastic strength, high ductility, fracture toughness are the properties considering for design process. Considering all the results of the materials, we can conclude that aluminum foam, Kevlar are suitable ballistic protection system. They can resist the high projectile efficiently. IJERT 10 is 060190 www.ijert.org 445. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Reference 1 Armand Lewis, Mattapoisett, Ma, U.S., Yongke Kim, North Dartmouth, Panel for Absorbing Mechanical Impact Energy and Method of Manufacturing, PUB No. US 2016/03682440A1, US 201603.682440A1 December 22, 2016 2KL Edwards, C.A. Abel, M.F. Ashby, Optimal Selection of Composite Materials in Mechanical Engineering Design Engineering. Design Center, University of Cambridge, Department of Engineering, Trumpington Street, Cambridge, CV21PZ, 3mm Chakri, G.H. Javadpur, Penetration Analysis of a Projectile in Ceramic Composite Armor Composites Research Laboratory, Department of Mechanical Engineering, Iran University of Science and Technology, Narmak, 16844 Tehran, Iran, January 30, 2007 4 M.V. Silva, D. Stainer, H. A. Al-Quraishi O.R.K. Montadu, and D. Hatza. Research article Alumina-based ceramics for armor. Application, Mechanical Characterization and Ballistic Testing, 2014 5 Yanfei Yangabi, Xiaogang Investigation on Energy Absorption Efficiency of Each Layer in Ballistic Armor Panel for Applications in Hybrid Design, University of Manchester, Manchester, UK, December 19, 2016 6 S.G. Savio, V. Madhu, and A.K. Gaggia, Ballistic Performance of Alumina and Zirconium Toughened Alumina Against 7.62 Armor Piercing Projectile, Defense Science Journal, Volume 64, Number 5, September 2014, pp. 477-483, doi, 10.14429/DSJ.64.6745 2014. IJERT 10 is 060190 www.ijert.org 446. This work is licensed under a Creative Commons Attribution 4.0 International License.